Lorenzo, and
Okay.
thank you, Lorenzo. And well, it's a pleasure to have Alejandro Kocsard, who is going to speak about periodic point-free homeomorphisms in dimension 2. So, Alejandro, if you want to start. We can hear you. Alejandro, you're okay.
No, okay. Sorry, I clicked twice. Okay. Now it's okay. So thanks very much, Fabio, for the introduction, and Lorenzo for the invitation. It's really my pleasure to have this opportunity in the middle of such a difficult situation. So let me share with you the slides here. Okay, so I think you can see the slides. Let me start with a problem that has been in the background of my research for a very long time, probably since the time I was a PhD student at TIMPA, which is a weak form of the CR closing lemma. So the problem is the following. We know in dimension 2, the only manifold, the only closed surface supporting periodic point-free diffeomorphisms is the torus, the only orientable surface. And the question is, if even though there exists some diffeomorphism without periodic points, even though it is true that the set of those diffeomorphisms with periodic points is CR dense in the CR topology. Okay. Well, I discussed a lot about this problem with Wellington de Mello, who was my PhD advisor, and with Enrique Pujals, who was some kind of unofficial co-advisor. And of course, we thought that this problem should be very difficult, and we consider an easier version of this problem just regarding minimal diffeomorphism. Recall that a minimal diffeomorphism is a diffeomorphism where every orbit is dense in the manifold. And in this case, the problem is, okay, it is true that the set of CR minimal diffeomorphism has empty interior with the CR topology. As I said before, I studied and I think a lot about both questions. And unfortunately, of course, they have positive answer for R equal 1, and this is due to the celebrated Pugh's closing lemma. But both of them continues to be open for R larger or equal than 2. But even though they are still open, I think that after so many years, I learned many things about periodic point-free homeomorphisms and diffeomorphisms, particularly for minimal diffeomorphisms. Okay, so this is what I want to talk about today, about what we learned in these years about these systems. So to put everything in a context, let me start with something which is very well known. I hope it's very well known, which is the one-dimensional case, to the circle case. When you want to study homeomorphisms on the circle, usually you go to the universal cover, you consider a lift. And the first thing that you have to do is to recognize which homotopy classes contains periodic point-free. If you want to study periodic point-free homeomorphisms, you want to recognize what homotopy classes contain periodic point-free homeomorphisms. In the case of the circle, you have only 2 homotopy classes containing homeomorphisms, the class containing orientation reversing homeomorphisms and orientation preserving ones, and just the orientation preserving class contains periodic point-free homeomorphisms. So you can restrict to orientation preserving homeomorphisms, and we know that we can define the rotation number. Essentially what you do is you consider the lift, you consider the difference between the lift and the identity, and this define this delta function here, which is happen to be a Z periodic. So it can be considered as a function defined on the circle. And the good point about the circle is that if you integrate this function against any invariant measure, here M of F denotes the set of invariant measure for F, you always have the same value. In this case, I call this value rho. And this implies that if you, because of Birkhoff theorem, we know that if we calculate the Birkhoff average on every point, we will have always, in fact, we will have uniform convergence to rho in this case. And the good point, the usefulness of this delta function is that it's a cocycle. That means that the displacement function of the n iterate of the cocycle is equal to the Birkhoff sum. So, and this is the good point about this function here. But this is not only this is not the only important property for rotation number. There is another one which is stronger than the existence of the rotation number, which I call bounded rotational deviations. The idea is that if you consider any point and you take n iterates of the point and you compare the displacement, this is the displacement of the n iterate of the point x, this coincide, the difference between the displacement and the displacement with respect to the rigid rotation is always bounded by 1. This happens for any n and for any x. And of course, this property is stronger than just the existence of the rotation number. And this property here will play a key role here in this discussion. Another important property for when you want to study periodic point free homeomorphisms is that you have a unique minimal set. And this implies that this minimal set is the non-wandering set and the recurrent set, and all the dynamical interesting points are contained in this set KF. And if you put together this boundedness of rotational deviations to get, you use this property to study the dynamics of the minimal set, you can easily show that you have a property that I call rigidity here, that is that the dynamics of F restricted to this minimal set is in fact a topological extension. This minimal set is a topological extension of the corresponding minimal rotation. I mean minimal because, sorry, I didn't put here, but of course, when you have a periodic point free homeomorphism, this number rho is irrational, okay? So this is an irrational rotation. It means that this is a minimal homeomorphism, and your F is a topological extension of this irrational rotation. And in fact, the semi-conjugacy can be extended to the whole circle. This is another property of the circle. This can be extended so the whole homeomorphism F is a topological extension of the corresponding circle rotation. And another property that you have here is unique ergodicity. You have only, in the case that you have a periodic point free homeomorphism, you have just one invariant measure. So I hope this is very well known. This is classical. Most of the results are due to Poincaré. So the situation in dimension 1, the study of periodic point free homeomorphism is pretty clear, at least from the topological point of view. I don't discussing here the differentiable structure or nothing like that. So let's go to dimension 2, which is the context I want to consider here. So we will consider orientation preserving homeomorphisms. Again, I will consider a lift to the universal cover. And again, the first thing that you have to do is to distinguish those homotopy classes containing periodic point free homeomorphisms. if you use Lefschetz's fixed point theorem, you can show that there are infinitely many. This is the first difference with the circle case. You have infinitely many homotopy classes containing periodic point-free homeomorphisms. But if you consider just homeomorphisms up to topological conjugacy, you can index those homotopy classes with the integer k. In fact, if you up to conjugacy, any periodic point-free homeomorphism is homotopic to a linear automorphism of this form, where k is an integer number. From the dynamical point of view, there are only two big classes that you have to distinguish. The case k equals 0, of course, the case k equals 0 is the case when you have your homeomorphism is homotopic to the identity, and the case k different from 0, which is the so-called the then twist case, or when f is homotopic to then twist. And so I will distinguish these cases, and I will focus most of the time in the identity isotopy class. In the identity isotopy class, that is when k is equal to 0, you can try to imitate what Poincaré did in the one-dimensional case. You consider your displacement function, delta f, which now is set to periodic. So it's periodic by any integer translation on the plane. So you can integrate this function with respect to any variant measure. Again, this is a cocycle. So that means that you have all the properties, the displacement of f tilde n is equal to the Birkhoff sum of this function with respect to f. But the novelty here is that this, in general, this is not a singleton anymore. That means that in general, this is a convex and compact subset. Of course, it's not non-empty, but it's not, in general, it's not a singleton anymore. So you have to understand what happened with the rotation set. It's called the rotation set, and you have to learn to extract dynamical information from the rotation set, because it's not that obvious as in the one-dimensional case. Obvious in the one-dimensional case, remember that you have something which is periodic point-free if and only if the rotation number is irrational. Here, the distinction is not as clear as in dimension 1. And what you can do if k is different from 0, of course, you consider again the displacement function, which
Alejandro?
is, yes?
Can I ask a question, just a quick question?
Of course.
So you could also imagine taking an arbitrary point and looking at all the accumulation vectors of those.
Yes.
Yeah. And would
Yeah.
that be the same as this or different?
Yeah. Thank you, Amy. The point is the following. In dimension 2, if you take your function delta f and you consider all the accumulation points of Birkhoff average of this function here, in dimension 2, you get the same set. It is not easy to prove. It's not completely, it's not easy to prove this. And that is a result due to Misurevich and Simeon. But this is not true anymore in higher dimension. It is not true anymore in higher dimension. In higher dimension, if you take any dimension here, you always have a convex and compact subset if you consider this, but both sets does not coincide, don't coincide if you consider just accumulation points. But in dimension 2, they coincide. Yeah.
Thank you.
Okay, you're welcome. What happens when k is different from 0? Of course, you can consider exactly the same displacement function here, but the point is that this displacement function is not a cocycle anymore. So a priori, you could do the same you did in the identity isotopy class, a homotopy class, isotopy class and a homotopy class here in dimension 2 is the same, but not in higher dimension, but here is the same. But the good point is that the second coordinate, this is the second coordinate of the displacement function, the second coordinate is a cocycle. So it is better to integrate this just the second coordinate. Of course, different methods can have different integrate here. So here you don't have, it is not useful to consider the compact subset in dimension 2, but it's really useful to consider just the compact segment that you get just integrating the second coordinate here.
Alejandro, sorry,
okay?
why is the second coordinate that important?
Here, because you can look here, ik, when you multiply by xy, you have in the second coordinate, you have just y. So that means that in the second coordinate, when you have something which is homotopic to ik, in the second coordinate, you have y plus a periodic function. And this is really a cocycle. When you have in the first coordinate, you have x plus k times y plus the periodic function. And this is a mess. It's not a real cocycle.
Okay, thank you.
So the important point is that it's the usefulness of this is that the second coordinate is a cocycle. But yes.
What is this notation, please? PR2 is just the second coordinate.
It's the second coordinate. It's the projection on the second coordinate. Yeah.
Okay.
Okay. So, so here you have, these are the two really different classes. Most of the time I will concentrate on the identity homotopy class, that is k equals 0. The techniques are similar, but not exactly the same for k different from 0. Okay, so it's a different setting. Most of the time I will concentrate on the first case. Okay, so the next step, okay, let's try to look for some periodic point-free examples and some minimal examples in dimension 2. We will see that the variety of possible dynamics that you have in dimension 2 is much, much richer than in dimension 1, of course. The first case of it's very easy are just rotations. Okay, for any vector in R2, you have the lift with the rotation. In this case, you have that the rotation number, the rotation set is a singleton. It's just the point alpha. You know that it's periodic point free if and only if alpha is an irrational point, and it's minimal if and only if some people call non-resonant, some people call totally irrational. This is completely classical and well-known. And the situation is very easy, and in certain way, it's analogous of it's what happened in dimension 1. Essentially, you have only one, up to topological conjugacy, you have only this example. But in dimension 2, there are some new phenomena appearing here. The first one is, I want to consider, is reparametrizations, in fact, time t of reparametrizations of linear flows. So I want to consider a linear flow here. The vector field, the original vector field is the vector field 1 alpha. And I'm multiplying the vector field 1 alpha by function phi. In fact, phi can be infinity, C1. Okay, I don't care about regularity, but it's at least continuous. And you take f tilde to be the time t of the flow of x. Okay, and in this case, you can produce new examples, some new phenomena. In fact, if you take alpha an irrational number, you will have that you don't have periodic points for the corresponding homeomorphism. This is due to the fact that when alpha is rational, the flow is minimal. Okay, and in fact, you can show that for any alpha and for every phi, function phi, there exists a genetic set of times t such that f is minimal. But this happens for any minimal flow, okay? And what about the rotation set? And what about the properties, the dynamical properties of these examples? Well, Shklover and Fayad, independent, I mean, it's not a joint work. When I put a comma here, I mean the different works. Shklover showed that there exists some alpha and some, in fact, real analytic function and sometime t such f is minimal and weak mixing. So this is a new phenomena. You don't have this phenomena in dimension 1. And Fayad Bassam extended this result, showing that for any Liouvillean number and for a generic set of time, he extended. But what I want to consider here, this is a new class of examples. You have minimal and weak mixing examples, taking time t of reparametrizations of linear flows. Franks and Misirevich, they studied flows in the two torus and the rotation set of the time 1 of time t of flows in the torus. And the interesting point here is that if you have a minimal flow, the time 1 or the time t for t different from 0 is always a point. And this was proved by John Franks and Michel Misirevich. As I said, in a work that they studied the rotation set of flows in the two torus. So this is a completely new phenomenon, but the rotation set again, here is a point and here is a point. Let's go to other examples, interesting example, which is the skew products over irrational rotations. You take an irrational number and you rotate in the first coordinate with this rotation, and in the second coordinate you take a function. Of course, you have to impose certain restriction for the function phi in order to have a homeomorphism here. For instance, if you take phi to be C1, it is necessary that the partial derivative of phi with respect to y is larger than -1. In order to have a diffeomorphism, for instance, in the torus. But okay, here I'm just saying, okay, I consider a skew product over an irrational rotation. And what about, in this case, what can we say? Michel Herman showed that any example of this form is in fact what we call a pseudo rotation. A pseudo rotation is nothing but a homeomorphism whose rotation set is a singleton. So here you have just a point. Okay, Michel Herman proved this. This kind of examples, there is a celebrated example of Furstenberg showing that there exists minimal but not unity ergodic, in fact, infinity diffeomorphisms of this form. In fact, it is in the case of Furstenberg, the function phi depends just on x and not on y. So it's a skew product where you have a rotation on each vertical phi. Okay, so again, this is a new phenomena. You have minimality, but you don't have unique ergodicity in the case of the two torus. And the last example, and again here you have just a point as the rotation set. So what happened in the last example that I want to consider is a skew product over a Morse-Smale diffeomorphism, which is something new in the sense that you can produce an example which is periodic point free. It is not minimal, but it's periodic point free. And the rotation set is can be a segment, not just a point. So let's see what happened here. I'm considering a skew product on the base, okay? 0 and 1/2 are the two fixed points of the north-south pole dynamics that I denoted by G. And I'm considering rotations. Remember, I'm writing in this, I'm considering on the fiber just rotations. And essentially what I can do is to choose different rotation number over 0 and over 1/2. And in this case, what you have is the rotation set will be a segment, a vertical segment. I'm here, F tilde, I'm considering the lift that fix 0 and 1/2. So that means that you have fixed vertical lines. That means that the rotation set will be 0. And the rotation set 0 in the first coordinate, but you have a segment, a vertical segment in this case. So this is the new example in the case of a periodic point-free homeomorphism with a rotation set which is not just a point, but as you can see, you have, this is an interesting phenomenon that I said before. In dimension 2, it's not that easy to extract the dynamical information from the rotation set, because here you can see that you have infinitely many rational points on the rotation set, even though you can produce example with no periodic points, because if you take irrational numbers over 0 and over 1/2, you will have something which is periodic point free. But in this case, you have wandering points. And in fact, this is something that you cannot avoid, and I will explain better this in a very few slides, yeah, in the future, shall we? Okay, so these are four families of examples that I want to consider. So what can we say about minimal or periodic point-free homeomorphisms or minimal homeomorphisms in dimension 2? So the main, and here, sorry, I forgot this. It is important to notice that in this case, there are two things which are very important, that in all the cases I mentioned here, we have an invariant foliation. And in most of the cases, we have the rotation set is a singleton. And these are two aspects that I want to point out, because I want to discuss in more detail this. So what can we say about periodic point-free or minimal homeomorphisms in general in dimension 2? Let me state the main result I want to discuss here. I like very much because it's very short. It's very easy to explain. And it's the following: is if you have, sorry, here it's orientation preserving. In fact, I think it's called in this way, but okay. If you have a minimal homeomorphism, then you have a dichotomy. Either it's a topological extension, that means it's semi-conjugate to an irrational circle rotation, or it is topologically weak mixing. And this is the dichotomy I want to show. And in fact, this is a work in progress. This is not completely done. In the case that you are not in the identity homotopy class, in fact, you always have a topological extension of an irrational circle rotation. This, I have the whole strategy to this last part, but there is a point which is not completely obvious, some details that I have to check. So let me recall what does topologically weak mixing mean. The idea is that you say that if you are in a manifold, in a topological, in a metric space, for instance, M, you say it's topologically mixing if every open set becomes epsilon dense for certain iterate. Okay, this is topologically mixing. So of course, you cannot have both conditions here because rational rotations are not topologically weak mixing, but you have this dichotomy. But more important than the result itself, I think it's I will use this result as a roadmap to discuss several results about minimal and periodic point-free homeomorphisms, to make a survey. I think the good point about this result is that you need to make a collection of several results, and it can be used as a roadmap to talk about periodic point free in certain cases and minimal homeomorphism in other cases. So this is the main result. Let's start this trip trying to understand these maps, minimal homeomorphism and more generally periodic point free homeomorphisms. So the first question is, okay, let's recall what is the rotation set. The rotation set is the integral of the displacement co-cycled against any invariant measure. And we want to understand what can we say about the rotation set when the periodic, when there is no periodic orbit, okay? So you consider this set here. That means that you have three possibilities, okay? This is a compact, convex, non-empty set. That means that you have three possibilities. The rotation set is either a point, a segment, or something, the rotation set has non-empty interior. In the first case, you have, I want to distinguish two possibilities. The case that the rotation, the only rotation vector is a rational point, and when it is irrational. The segment, we will see that there is a first, you have to distinguish the rational slope and the irrational slope case. And in both cases, you have to see what happened with rational points. If the rotation set contains rational points or does not contain rational points, and here the same. Okay, and so what I want to understand is in which cases there is some periodic point free homeomorphisms in these different classes. Okay, so the first one here, if you have just the rotation set is just a point, and this point is rational, then you have periodic points. Okay, and this was proved by Misiurewicz and Simian in the paper I mentioned when Amy asked me about the accumulation points of the Birkhoff averages. They proved that in fact any extremal point of the rotation set which is rational is realized by a periodic orbit. So of course, if you have a point, it's an extremal point. Another case is when you have rational slope, the segment with rational slope, and you have rational points there. Remember, this is the situation when I consider the skew product over the North Pole, South Pole dynamics, when we have a vertical segment and you have infinitely many rational points inside. Well, the idea is that if you have a periodic point free and you have such a rotation set with rational slope and rational points, then the non-wandering set cannot be the whole torus. This was proved by John Franks in the case of area preserving homeomorphisms. We extended this with Andrés Koropecki to the non-wandering case. And Pablo Dávalos, in his thesis, PhD thesis, he characterized the dynamics that you can have in this situation when you don't have periodic points. And essentially, he showed that the situation is very similar to what I showed of the skew product. It's not really skew product, but you have annular continua, which are either attractor or repellers, or you have something which is semi-attractor or semi-repeller. But I mean, you cannot have this, and the dynamics in this situation is very well understood if you suppose that you don't have any periodic point. So if you want to study minimal homeomorphisms, or if you want to understand periodic point free homeomorphism with where the whole space is non-wandering, then you can forget about this. On the other hand, you have the result of Jonker and Chang. They showed that if the slope is irrational, then the periodic, if the slope is irrational, you can only have one rational point inside the rotation set. Or none. I mean, but if you have one rational point, then this rational point is realized by a periodic orbit. So again, here you have a periodic orbit. And here, if you have no empty interior, then first, Michael Handel showed that there exist some periodic points. And after that, John Franks showed that, in fact, any rational point in the interior of the rotation set is realized by a periodic orbit. So, of course, here you have periodic points. So that means that if you want to study for instance, no wandering periodic point-free homeomorphisms, or if you want to study minimal homeomorphisms, you can restrict to the following cases. When you have the rotation set is a point, and this point is irrational, I mean, it's not a rational point. When you have rational slope, and you have no rational point in the rotation set, or if you have irrational slope, and here again. So that means if you have a segment, you can consider that you have no rational point. And I want to focus in these cases here, because this is part of a conjecture made by John Franks and Misha Mishurevich in that paper I mentioned before about the rotation set of torus flows. So I don't want to discuss a whole conjecture, but in the case that you have a one-dimensional rotation set, John Franks and Misha Mishurevich, they conjecture that this cannot happen. They said that if you have a homeomorphism such that the rotation set is a segment, you cannot have you necessarily have rational points inside the rotation set. This is just, in fact, it's more detailed, the conjecture of John Franks and Misha Mishurevich, it's more detailed, but I just want to make this brief version of the conjecture. And this was proposed at the beginning of the 90s. And in something like 6 years ago, Artur Avila constructed an example of a Sinfinity minimal area preserving diffeomorphism, where the rotation set is a line segment and it has irrational slope. Okay, so he provided a counterexample to the conjecture because, as I said before, if you have something which is minimal and the rotation set cannot contain rational points. So if it's minimal, it's completely, it eliminates this possibility. So he provided a conjecture he provided a counterexample to the conjecture in the case of irrational slope. And the rational slope continues to be open. And we expect that the conjecture should be true in the case of rational slope. Well, I will mention the ideas of the proof because I proved some part. Martin Sambarino, Alejandro Pasegui, and Andres Koropeki, they proved the other part that essentially proved the conjecture for minimal homeomorphisms in the sense that if you have a minimal, there is no possibility of having a minimal homeomorphism with a rational slope segment. And we are extending, this is a work in progress, we are extending this result with Fabio to the non-wandering case. Okay, eliminating the minimality assumption here and just considering non-wandering case, but this is a work in progress. So there exist examples with of minimal homeomorphism, diffeomorphism. In this case, here the regularity is not an issue in this point, where the rotation set is a segment. And what about the invariant foliations? I mentioned that I want to focus in two different things. One is the rotation set and the geometry of the rotation set, and the other thing is the existence of invariant foliations. Well, I mentioned in the first 4 families of examples, in all the cases you have invariant foliations. So when I started looking for examples and studying minimal homeomorphism and diffeomorphism, I said, okay, maybe any minimal diffeomorphism has an invariant foliation. But you study this space. This space is the, you can call Anosov-Katok space, or, well, it's the infinity closure of the smooth conjugacy class of rotations on the torus. Let's say that any infinity minimal diffeomorphism we know so far belongs to this space, and of course it's part of the very difficult conjecture saying that all the examples belong to this space, but we don't know. But Albert Fathi and Michel Armand, they proved that minimality and unique ergodicity are generic properties in this space here, in the Anosov-Katok space. And then with Andres, we showed that the non-existence of invariant foliation is another generic property here. So that means, of course, that means that you have a lot of minimal, uniquely ergodic diffeomorphisms with no periodic, with no invariant foliation. Okay. And how you can prove this? And when I say invariant foliation, I don't mean, I don't care about the regularity of the foliation. There is no topological foliation. And how you can prove this? Which is the argument to destroy the existence of invariant foliations? The key argument is the following. Invariant foliation implied bounded directional rotational deviations. What is that? What does bounded directional rotational deviation mean? Recall what happened in dimension 1. In dimension 1, we had that any spherical homeomorphism exhibit this property here. That means that the orbit of any lift and the corresponding orbit of the rotation, they go together up to an error smaller or equal than 1. This happened in dimension 1. Well, if you consider a foliation on T2, there are only two classes of foliations in T2, foliations, I mean, without singularities. There are only two classes of foliations in dimension 2, which are those foliations containing a wrap component and those foliations which are suspensions of circle homeomorphisms. In both cases, you can easily show, because of this property here that I mentioned here, you can show that if you have a foliation in T2 and you lift the foliation to the universal cover, then there exists a vector V, and it's not important that it has norm 1. The important point is non-zero, and there exists a constant C, such that every leaf of the foliation is contained in a strip of width C. For any leaf, you can find a strip of width C such that the leaf is contained in the strip. And here V is the perpendicular direction to the sides of the strip. And you will see why I'm considering the perpendicular direction. Okay? So this happens for any foliation. And what happens if you have an invariant foliation? If you have a homeomorphism exhibiting an invariant foliation, the idea is that this property of the leaves, this geometric property of the leaves, translates to the dynamics in the following sense, that if V is the direction perpendicular to the strips, this direction is unique up to multiplication by -1. Okay, I mean the direction is unique. In this case, the rotation set can be either a point or a segment. These are the only two possibilities that you have. And in fact, in any case, the rotation set is contained in a line which is perpendicular to V. And you will have, if here you have the constant C, here you have another constant C prime. I don't care about, you can compute an estimate of this, but you can show that there is a constant C prime such that you have this property here. What does mean? This is the rotational deviation. You cannot have, in this case, for instance, if you have a segment, you cannot have bounded rotational deviations in any direction because you have points with different rotation vector. But if you project everything on the V direction, okay, all the points have the same rotation vector with respect to the projection on V. This is what I'm doing here. And what I said, if I have an invariant foliation, then necessarily what I have is this boundedness for rotational deviations in the V direction. Okay, so this geometric property translates to a dynamical property here. And so this is the idea how to prove that there is no invariant foliation. Essentially, what you have to do is to show that you have unbounded rotational deviations in any direction. And in this way, you can assure that there is no invariant foliation. Okay, this is the idea we use with Andres in that paper.
Excuse me.
Yes.
So by invariant foliation, you mean each leaf is fixed?
No, sorry. The image of each leaf is another leaf or another one. I mean, the whole foliation is invariant, not each leaf. Okay?
Okay, thank you.
So we have seen that if you have invariant foliations, you have bounded V deviations. V deviation means exactly that it's deviations in the V direction, okay? So if you have an invariant foliation, you have bounded V deviations. What about the reciprocal statement? Well, the idea is reciprocally, if you have a homeomorphism with no periodic point and it's non-wandering, you can show that you can show that bounded V deviation is equivalent to the existence of an invariant pseudo-foliation. You cannot show that it's a foliation. In fact, there is a very nice construction due to François Béguin, Sylvain Clovissier, and Tobias Jäger. He constructed a minimal diffeomorphism of the two torus, which is semi-conjugate to an irrational rotation, and each fiber of the semi-conjugacy is a pseudo-circle, which is a very nasty continuum. And in this case, the pseudo-foliation is the decomposition of the two in these pseudo-circles. So I will give a definition of what a pseudo-foliation is, but the idea is that both properties are equivalent. And in fact, if you have, I won't prove this, but the idea is that when you have a torus pseudo-foliation, again you have a direction V, which is perpendicular to the asymptotic direction of the ellipse. And the case that V has rational slope, you can show that the ellipses are compact, or the pseudo-ellipse, let's call, are compact. And in this case, what you have is your homeomorphism F is a topological extension of an irrational circle rotation. This is a content of what I recently proved. The first part I proved with Pereira Rodriguez, who was a student of mine. And this second part, it's a preprint that I recently put in the archive. So what is a pseudo-foliation? A pseudo-foliation, a plane pseudo-foliation, is a partition of R2 such that every atom is close, connected, and in most of the cases you can suppose they have empty interior, but the key property here is that every atom of this partition disconnect the plane in exactly two connected components. Okay, so it's a pseudo-foliation is something that if you look from very, very, very far away, it looks like a foliation, but the topology of the atoms, they are not necessarily lines, okay? And what is a torus pseudo-foliation? Well, essentially it's a partition of T2. You go to the universal cover, you lift the partition, and you take as atoms of the partition the connected components on the leaf, and you say that you have a torus pseudo-foliation on T2 if the leaf is a plane C2 equivariant plane pseudofoliation. And the good point is that this property is equivalent to boundedness of V deviations, and they are generalizations of geometric of classical foliation, but they are good enough to get a lot of properties, like in this case, to prove semiconjugacy, or we will see to prove weak mix, topologically weak mixing property. So in order to finish this talk, let me explain how you can use these objects these pseudofoliations, you can prove this to prove the main result of the paper, of the talk I wanted to discuss here. First of all, let's focus on the rotation set. In the rotation set, we know that we have to consider two possible cases, when it is a segment and when it is a point. Let's start considering the case it is a segment. So in this case, we have to consider the rational slope and the irrational slope case. So let's start supposing that it's a rational slope segment. And in this case, as I said before, in the case of minimal homeomorphisms, I proved that this implies boundedness of V deviations where V is perpendicular to the rotation set. Okay, so this is a picture that I mentioned before. I take V perpendicular to the line supporting the rotation set. And in this case, when you know that when it is a segment, and if F is minimal, I prove that you have boundedness of rotational deviations. And this is what the work in progress that I mentioned before with Fabio. We are extending this considering not just minimal, but non-wandering homeomorphisms. And the idea is that you use the boundedness of the deviations plus this property here. I mean, in this case, it's not necessary to consider minimality. In this case, we know that these two properties implies that this is a topological, this is a topological extension of an irrational rotation. Okay, sorry, here I forgot to, this is the last result. There are some previous results here due to dealing with the semiconjugacy due to Tobias Jäger. There are some work of Tobias and Fabio Tal as well, in this case of dealing with the semiconjugacy, starting from boundedness of V deviations together with this property here. And so in this case, you have a topological extension. You have a semiconjugacy and it's okay. And it is interesting that what I mentioned before, this having this property here, Andrés Koropecki, Alejandro Pasegui, and Martin Zambarino, they show that this implies that this cannot happen. In fact, this does not exist. And this proves the Franks-Misiorewicz conjecture in this setting, at least for non-wandering homeomorphisms. The remaining case, that is the rational slope segment, in fact, cannot happen here. What happened in the rational slope segment? The first part is the same. I mean, when you have a segment, in fact, in general, you expect to have boundedness, the V deviations with V perpendicular to the rotation set. In this case, you have this again. But the novelty here is that this implies that you have a pseudofoliation, but this pseudofoliation has an irrational asymptotic homological direction. And since you have points with different rotation vectors, you have a shear along the ellipse. And using minimality, you can show that this shear happens if you take any open set. You have points with different rotation vectors, and they have to shear along the ellipse. This is and you can show that the ellipses are minimal. The ellipses are dense, And in this way, you can prove the minimality of the pseudo foliation, let you show that you have topologically mixing, not just topologically weak mixing, by topologically mixing. And just to finish, now assume that you have a point. The rotation set is just a point. If you have unboundedness v deviation for every direction, you can prove that minimality implies topologically weak spreading, which is a property stronger than mixing. This is something we defined with Andres. In that paper, we deal with invariant foliations. In this part, sorry, I have to say that this part here is the more technical one and the most difficult one. Of course, this is the same. These are the most difficult. And this part here is rather technical, but and it has a lot of new ideas that I don't have time to discuss here, which is something I called the raw centralized Q product, or the Hamiltonian fiber-wise Q product, which is the novelty of these techniques here, but I don't have time to discuss. But this is a very key point of the argument. And this is what I mentioned before. In the case that you have boundedness with respect to a rational slope segment, this is what I mentioned that Tobias Jäger, this is something here, you need to put some additional hypothesis here. I don't want to enter into the details. In fact, in my last work, I removed even this hypothesis here, and I put some geometric properties of the non-wandering set, but it's not important. If you have non-wandering dynamics and some property that holds in the case of minimality, then you can show that you have a topological extension of an irrational circle rotation in this case. And if you don't have a rational slope direction, you just have an irrational slope direction against what you have in topologically weak mixing. And this is again using the pseudo foliation, which is an argument, as I said, it's very similar to the previous one. You have a minimal pseudo foliation, and you have deviations in the other direction, because if you have just an irrational direction, you don't have boundedness in the other, and that produces shear along the leaves, and this produces the topologically weak mixing. This is everything I wanted to talk about. Thank you very much.
So, thank you, Alejandro, for the presentation, for the very great presentation. And are there any questions?
So I couldn't tell if this is true or not, but are you suggesting that you could possibly replace minimal in the statement of your main theorem with non-wandering, or do you need plus homotopic to the identity or something, or do you need?
Yeah, okay, yes. In the case, if you remove the hypothesis of minimality, it is pretty hard to show topologically weak mixing, but you have some, I mean, as you can see here, you have to distinguish two cases: when you have boundedness of rotational deviation and when you have unboundedness of rotational deviation. If you have boundedness of rotational deviations and you have non-wandering dynamics plus some hypothesis that I mentioned that it's part of the last work I preprint, yes, you can repeat the same argument. But that it's pretty hard to show. I don't know if it is true. If you have the topologically weak mixing case, if you have unboundedness of rotational deviations, just having non-wandering dynamics, removing the minimality assumption. I don't know.
What about area preserving?
Area preserving, it's a good question. I'm not completely sure. I mean, for a long time, I thought that area preserving and no wandering from the topological point of view should be very similar. I don't think anymore it is true. A very good difference, I mean, you know, the CR closing, the infinity closing lemma for Hamiltonian diffeomorphisms that recently appeared of the Japanese guys. I forgot the name, sorry. And it is funny that they prove a very strong infinity closing lemma for Hamiltonian diffeomorphisms, but it is completely open in the case of the torus for area preserving diffeomorphisms. So I don't know. It's it is not clear. I don't think it's area preserving is very helpful for the topological setting. But
Hamiltonian,
I'm not sure.
What about
Sorry?
Hamiltonian? But what about Hamiltonian?
No, Hamiltonian. That's the point. That's the point. Hamiltonian diffeos are outside this scenario because they have fixed points. You always have fixed points for Hamiltonian diffeos.
And homeos as well?
Even Hamiltonian, yes, because the definition, there are several definitions of Hamiltonian homeos in T2, but the most natural one is that the rotation number of the rotation vector of Lebesgue is 0. And if you have 0 of rotation vector of Lebesgue, you automatically have a fixed point. I don't remember exactly. I think it's due to Jean-Franc's that result.
I think so. Thanks.
You're welcome.
I have another question, Alejandro. So you showed mostly the ideas for the case of where you're homotopic to the ID. Does it change a lot when you do it for dent twists or for the cases homotopic to dent twists?
Yeah. Essentially, I mean the theorem holds for the theorem holds almost the same for homotopic to dent twist. The good point about dent twist is that you cannot have. I think that you cannot have the topologically weak mixing case in that. And that's the point that I have some issues in the argument, but I think that the general strategy is okay. The big difference is that you have to modify the definition of that row centralized Q product I mentioned, that I didn't define here, but I mentioned. And I think that essentially in the dent twist case, I think that you cannot have unboundedness rotational deviation. Okay, so if you have a minimal homeomorphism homotopic to the identity, you know, you Salvador and Garcia, you prove that you have just a point as a rotation set, an irrational in the case of dent twist. And I think that in that case, you always have boundedness of rotational deviation. And I have a strategy of the proof, but there are some arguments which are not completely done and completely clear. But yeah.
Thank you. So,
sorry, Alejandro, I have a question. I don't know if it's a very silly question. When you define a pseudo foliation, I think that the main point is that the leaves disconnect the space. Why is that important? It's possible.
First of all, what you want to have is the you want to have an asymptotic direction, something similar to what happened in for real foliation, for foliations, true foliations in the two torus. And if you disconnect, if you have an atom which does not disconnect R2, this is essentially a singularity of the foliation, because it should be contractible. If it's close, connected, and does not disconnect, that means that it's contractible. So if you look from very far away, it looks like a singularity.
Okay.
And you don't want to have singularity because it's a mess.
I thought that you were the mess.
You get a fixed point at least. You get a periodic point. No?
Yeah.
You will not be periodic point free if you have a leaf which does not disconnect the plane.
No, sorry. You can have something completely different, which is not a foliation. You can have a partition of R2 such that every atom, it's not a point, but it's connected, it's closed. Well, some of them could be a point, okay? But some of them are not a point and they don't disconnect. This is what happens if you have something which is semi-conjugate to an irrational rotation and it's not conjugate. And in this case, the fibers can be connected, okay? And this is not really a foliation. I mean, you don't want to call that a foliation.
Okay, thank you.
It's a partition in compact sets which are not, I mean, they don't deserve the name to be a foliation.
Pseudo foliation.
Yeah.
So, well, I have one question. Is you've been working for a long time on the two conjectures you started the talk with. So, what do you believe it's true?
What I believe, yeah. In this moment, I think the question A is completely open. We don't have any idea. Question B about minimal diffeomorphism, I think is doable in the next few decades. But question A, I don't have any idea, any real idea or any strategy. But yes, question B, it seems to be more doable. No.
So, there are any other questions? So,
I have a question. Maybe it's a silly and old-fashioned question. What happens if you have an structurally stable diffeo? Do you know if you can answer that it has a periodic point or something like this?
Exactly. Well, okay, great. That's another question I discussed a lot with Enrique and Wellington during the PhD. We put it a lot of additional hypotheses: structurally stable, uniquely ergodic. We don't know. I mean, if you can have something which is infinity, even though this is another good point. In fact, I discussed that problem with Katok sometime. That I said that in the book, the Katok-Kocsard Black book, they say that they define structurally stable with taking homeomorphism because it doesn't make any sense to take diffeomorphisms. But in fact, the problem makes sense. You can have something which is a infinity diffeomorphism such that there exists a neighborhood. Everybody in the neighborhood is infinity conjugate to the same diffeomorphism. So that means that you have a infinity structurally stable diffeomorphism. such that the conjugacy is infinity. And of course, if you have such an example, it should be periodic point free, but we don't know. That problem continues open. I think that was a conjecture of Michel Herman, if I'm not completely mistaken. That there is no infinity structurally stable diffeomorphism such that all the conjugacies are infinity.
Hey, thanks.
Okay, so let's thank Alejandro again.
Okay, thank you.